Great, so we're going back to obfuscation, and Noam will tell us about lower bounds for obfuscation.
Thanks. Thanks for inviting me. So yeah, we are going back to obfuscation, but most of the talks on obfuscation we've seen in this workshop was on constructing obfuscation. I want to prove impossibility results for obfuscations. And the goal is to understand what is the minimal overhead of obfuscation. So in obfuscation, the input to the I/O is a Boolean circuit, and the I/O outputs a Boolean circuit, C prime. And the question is, can C prime be roughly of the same size as C? Or what is the efficiency of the obfuscated program compared to the original program that we started? And to have like a fair comparison between the running time, I want to compare it in the same model. So the model of computation is actually very important. And for me, I'm going to assume that both C and C prime, both the input and the output of the obfuscation, are Boolean circuits with NOT, OR, and AND gates with fan-in at most 2. So this is going to be important. And of course, if P is equal to NP, we have very good obfuscation. We have obfuscation with no overhead at all. The output circuits of the obfuscation is of the same size as the original circuit. But the question is, assuming that P is not equal to NP, that we have some hardness, can we prove some lower bound on the size of C prime? Can we prove that C prime must be at least 1 plus some constant times the size of C? And we do not know how to prove it. We don't have any like such lower bound on obfuscation. In this talk, I'm going to present like a weak lower bound. I'm going to show that obfuscation for multi-bit circuits, if the input circuit can output more than 1 bit, must have overhead of 1 plus 1 over log C. So this is like a very weak lower bound, but this is the best lower bound we have on obfuscation. And like I think one of the goal of this talk is to like raise up this question of proving lower bounds of obfuscation. I think people didn't think about it much. So maybe it's simple to prove like better lower bound. And the second thing I want to emphasize is in this talk is the techniques. So the way we prove it is via a connection between cryptography to this thing that some of you may be heard of, which is meta-complexity. Okay, so. Yeah, so it's not clear. So you need to care both on the length of the encoding of the Turing machine and the running time of the obfuscated program. So I care of both of them. Okay? And like you can ask what is the overhead in both parameters. And
so to show that there exists a C for which you have this?
Yeah, I'm going to show a specific C for which we cannot obfuscate it.
So you're viewing obfuscation as something that like takes as input a circuit and outputs a circuit. If I instead view obfuscation as something that like takes input a circuit and outputs like a description that I then feed into.
Yeah. So usually in the construction, if you look on constructions, then the obfuscation of the circuit outputs some program pi, and then you have like a val algorithm that takes pi and x and outputs C of x. And there are works that minimize the size of pi compared to the size of C. Like you can show that the size of pi is at most 2 times the size of C. This is AGS. But the running time of this eval is some polynomial. So if you try to construct a circuit from it, the circuit can be actually very large. Okay, so I care about the true efficiency, like in the same model as the original circuit.
What is the security parameter in the?
Yeah, so for this I'm ignoring the security parameter. In our true lower bound, like there is a plus additive, like any polynomial in the security parameter. So we can rule out any obfuscation in which the dependent in the security parameter is polynomial.
I see. So epsilon doesn't depend on security parameter.
The epsilon doesn't depend on the security.
Okay.
So now, in this eval model where you have the description, we know 2 from this AJS work, but probably heuristically we assume 1 should be achievable, right? Like.
Yeah.
So here you're saying 1 cannot be in the circuit model.
In the circuit model, yeah, exactly.
I guess you'll probably tell us about it, but I feel like for all, I mean, if you just consider only ASIF circuits, then probably this, or do you think, what do you think? It's probably not evasive, but for all evasive circuits, I suspect that maybe.
What do you mean by evasive circuit? Sorry.
Circuits which kind of like family circuits, you draw a random circuit, it's mostly zero. It's mostly out of zero.
Yeah. Yeah, I don't know. The circuit that we see have like a specific structure that then we will use this structure as stronger. Yeah.
So it's not Boolean circuits, right?
Okay, so the technique is via connection between cryptography and meta-complexity. And like the original question we try to understand is actually a question in meta-complexity. And in meta-complexity, there is this problem that I will talk on, which is called the minimal circuit size problem, MCSP, which is like an important problem in meta-complexity, and we do not know if this problem is NP-complete. This is like a major open question in meta-complexity. And what we try to understand is why this problem is not, we do not know that this is NP-complete. What we showed is that if we have obfuscation, then this problem cannot be NP-complete with respect to some kind of reductions. And this is like what we wanted to achieve. We wanted a barrier on NP-completeness of this problem. But then we looked on this result and thought that maybe we can look on it from the other direction. So this result means that if we will be able to prove that gap MCSP is NP-complete, we will show that there is no obfuscation. Because if we have obfuscation, this problem cannot be NP-complete. So if this problem is NP-complete, there is no obfuscation. Of course, unfortunately, we do not know that this problem is NP-complete. So
this is NP-complete using your type of read.
Yeah, for a specific type of reduction. I will talk about it with more detail. Okay? Yeah, but you're right. So we do not know that this problem is NP-complete. So for sure, we do not know if it's NP-complete with our type of reductions. So we cannot rule out obfuscation, unfortunately. But we get lower bounds on obfuscation because we do have some other problems with similar structure that we do know that they are NP-complete. So what I want to emphasize is that this connection between meta-complexity and cryptography gives us a result, like a pure result in cryptography that doesn't talk about meta-complexity at all. And I think it's interesting. So let me talk about this problem, gap MCSP. So the minimal circuit size problem is the following problem. We get as input a string of length n, and we think about the string as a truth table of a function from log n bits to 1 bit. And the question is, what is the minimal size of a circuit C from log n bits to 1 bit that computes the function that is described by this truth table T? So for example, if we have this truth table, we can represent it by this string 0, 1, 1, 1. And in this case, this string represents the OR function. And we ask what is the minimal size of a circuit that computes this function. So in this case, this is just the OR function, and the answer is 1. So this is the minimal circuit size problem. And in gap MCSP, we have two parameters, two integers, S and L, where S is smaller than L. And the goal is given a truth table to distinguish between the case in which this truth table cannot be computed by a small circuit to the case in which this truth table cannot be, between the case in which we can compute this function using a small circuit to the case in which we cannot compute this function by a larger circuit. So we need to distinguish between the case in which there is a circuit of size S that computes this function to the case in which there is no circuit of size L that computes this function. And it's not hard to see that this problem is in NP because the witness to this problem is just the small circuit that computes this function. The input is the truth table, so we can run in polynomial time in the truth table length, so we can just enumerate over all possible inputs, check that the circuit computes the right function. So this problem is in NP. And also, if we assume cryptography, if we assume one-f functions, then this problem is hard. Because if we have one-f functions, we have pseudo-random functions. And if we have pseudo-random functions, we have functions that we can compute with a small circuit, but are indistinguishable from random functions that cannot be computed using a small circuit. So assuming cryptography, this problem is out. But the question I want to talk about is this problem NP-hard? And we do not know. This is like an open question since the 60s and major open questions. We do know that some variants of this problem are NP complete. So for example, Raoul showed that if you consider circuits with random oracle gates, then we can reduce SAT to it. This language is NP complete. And Irahara showed that if we get a truth table in which in some of the entries we don't care what is the value that the circuit output, then also we can show a reduction. We can show that this problem is NP complete. But for gap MCSP, as I defined it, we do not know what the answer is. And we have barriers on proving the NP completeness of this problem. So we know that proving the NP completeness of this problem is going to be hard. And what we showed in this work is that we have a new barrier on proving the NP completeness of this problem under so-called Levin reductions. Okay, so I want to define what Levin reductions means.
So multi-CSP, MCSP, that's for circuits that have multiple outputs, correct?
Multi-MCSP is circuits that...
You are considering circuits from n inputs to n outputs.
Yeah, so this is exactly how we will get it over. Okay, so we'll talk about it later. So what are Levin reductions? So let's start from talking about polytime reductions, the usual way in which we define NP completeness. So the way we usually define NP completeness is using many-to-one reductions or CARP reductions. So I will define CARP reductions from SAT to gap MCSP, which is the reduction we need in order to prove that gap MCSP is NP complete. Such a reduction is simply an efficiently computable function that take an input for SAT, a SAT formula, and output an input for gap MCSP, which is just a truth table. And the promise is that this formula phi is in SAT if and only if this truth table is in gap MCSP. Meaning that if we have a witness that satisfies this SAT formula, there is a small circuit, smaller than S, that computes this truth table. And if we do not have a witness that satisfies this formula, there is no circuit of size L that computes this truth table. In other words, if there is a circuit of size L that computes this truth table, we have a witness that satisfies the formula. This is CARP reduction. Levin reductions are CARP reductions with a constructive proofs. So Levin reduction is just a triplet of functions, f, g, and g prime. F is the CARP reduction, and g and g prime is just the constructive proof. So g is a function that takes a witness for SAT, output a witness for MCSP. G prime is a function that takes a witness for gap MCSP, output a witness for SAT. This is CARP reduction. And this is like, actually this is the usual way we think about reduction. We prove reduction. This is the natural way to prove reductions. As a result, most of the reductions we know are Levin, and this includes the proof of the PCP. The PCP theorem can be proven using Levin reductions. And also in cryptography, we need this kind of reduction. If we reduce some NP problem into graph coloring in order to prove in zero knowledge proof this language, then we need to be able to take a witness for the original problem and to convert it into a witness for tree coloring. And the same for the other direction, for example, for a knowledge extractor. So we need Levin reductions in cryptography. They get both the instance and the witness. Yeah.
Sorry, what's the difference between CARP and Levin again? I missed.
So CARP is just the mapping reduction. Levin is also the constructive proof.
Witness is mapped to it.
Yeah.
Yes, okay.
So we have a way to take witness and convert it into a witness.
Are there any known examples of things not Levin reduction?
So I only know on randomized reductions which are not Levin. For example, the proof of the isolation lemma. You take the witness, apply an hash on it, and if you just apply the hash without knowing the witness, you get another hash. So there are randomized reductions that uses like probabilistic method in the proof, but otherwise deterministic I don't know on any such reduction.
Well, there are some reductions which use multiple covariates.
Yeah, of course. Only talked about CARP reductions.
Randomized short circuit problem. It's
randomized. Yeah.
Randomized, but even if you were it's not clear if you remove the randomness, still how do you map the.
Yeah. Okay, so now the question is gap MCSP Levin NP-complete? Is it NP-complete with respect to Levin reductions? And what we showed is that under cryptographic assumptions, and for large enough gap MCSP is not NP-complete with respect to Levin reductions. And the same is true for like randomized reductions and non-uniform reductions and reductions that can run with sub-exponential time, assuming the right cryptographic assumptions. What are the cryptographic assumptions? So we have two assumptions. One is a very mild assumption, basically that NP is not equal to P. We'll talk about it later. And the second is obfuscation.
This is new result? That's your new result?
This is the one of our new results, yeah. Okay, so assuming obfuscation for large enough gap MCSP is not Levin NP-complete. And I do not need to define obfuscation in this workshop because this is a workshop of obfuscation, but I will just say like obfuscation for me is a procedure that takes a circuit, output a new circuit that hides the internal implementation of the original circuit. And using obfuscation, we can construct many useful primitives using the fact that we have obfuscation and the assumption that NP is hard. We get one-way functions, public key encryptions, multi-party computations, and much more. But like this ugly drawing hides the fact that the obfuscation makes the circuit larger. So it can take a small circuit and output a larger circuit. And this is the overhead of the obfuscation. The ratio, the relationships between the output of the size of the circuit that the I/O outputs to the original circuit.
So you're assuming there is an I/O with low overhead.
I will talk about the overhead. So the overhead is at most polynomial. And the result is going to be that if you have I/O with overhead P for some polynomial P, gap MCSP with the same gap is going to be not Levin NP-complete. So this is actually what we prove. And before showing you the proof, which is quite easy, I want to say that assuming obfuscation, gap MCSP is actually, in some sense, NP-complete. If gap MCSP is easy, then also NP is easy. And this is just because if you have obfuscation and NP is not easy, then we have one-way functions. If we have one-way functions, we have pseudo-random functions, and gap MCSP is hard. So if NP is hard, gap MCSP is hard. And if gap MCSP is hard, then of course also NP is hard. So this is if and only if. So the only thing that this says is that it's going to be hard to prove the NP-completeness of this problem, but it's actually in some sense NP-complete. Okay, so I want to show you the proof of this theorem.
So you're saying it doesn't exactly say that it's NP-complete, but let's say
yeah, in some sense.
Then you're saying that it would be hard to prove it NP-complete with a constructive proof.
With a constructive proof, yeah. Like CARP reduction with a constructive proof.
Does it lead you to think that you could do it with randomized?
So this also like includes randomized Levin reductions, but maybe you can do it with like many queries reductions or like. Okay, so the idea of the proof, we are going to assume, for this talk, I'm going to assume obfuscation, and I'm going also to assume a collision-resistant hash function. That for me, collision-resistant hash function is just a single function which is shrinking, so there are many collisions, but it is hard to find any specific collision. And in the proof, I'm going to show you in the proof, and you can see that we actually do not need collision-resistant hash function. It's enough to use target collision-resistant hash function or universal one-way hash function, primitive that can be constructed from one-way function. So we can replace this assumption with the assumption that NP is out. But in the proof that I'm going to show you, I will just assume that I have collision-resistant hash function. And the idea is to use the Levin reduction together with the obfuscation in order to find a collision in the collision-resistant hash function. So I'm going to assume that I have a Levin reduction, an obfuscation, and a collision-resistant hash function, and I'm going to break the security of the collision-resistant hash function. And the way I'm going to do it, so first I'm going to define for every image of the hash function a SAT formula. For every y, I'm going to define phi y, which is the SAT formula that on assignment x prime, output 1 if and only if age of x prime is equal to y. So it's just implementing age with a circuit and outcoding y into the circuit such that the SAT formula will output 1 if and only if age of x prime is equal to y. And then I'm going to sample a random x, compute the image of x according to the hash function, and apply the reduction from phi y, when y is my image, to GAP MCSP. So I have a SAT formula, and I'm applying the reduction to get a truth table of a function, and the promise is that this SAT formula is satisfiable if and only if there is a small circuit that computes this truth table. But I know that this SAT formula is satisfiable. I have a witness x. So I have a witness x. I can use the Levin reduction to get a small circuit that computes this function described by this truth table. Now,
how large is the truth table?
The truth table is, so I'm going to assume that it's of length like same as the SAT formula, but like, this is like, let's say it's of size n, like for some n. Like what is the?
On all x's, I don't understand. T consists of all possible x's.
No, I'm starting from x of length n. Okay, so some specific length. I want to find a collision for this security parameter. Okay, I'm ignoring the security parameter.
So the truth table is on what elements? Not on all. It's not on all n 2 to the n assignments to x.
No, this is the output of the reduction for GAP MCSP. So this is some truth table. Okay, it's not the truth table of the formula. Okay. I'm applying a reduction to GAP MCSP, get a truth table.
Smaller. You move into a much smaller.
Yeah, it can be any polynomial. Okay. So I have a witness for this SAT formula. I get a witness for GAP MCSP, so a small circuit that computes this truth table. Now, the point is that for this SAT formula, there are many witnesses that satisfy it, because there are many collisions for the hash function edge, and any collision is a satisfying witness for this hash function. But the security of the CR edge promises us that we cannot find any other witness for phi y. But here, we have an efficient way to sample new witnesses. You can just apply the I/O on this circuit. So the I/O gives us a way to sample new witnesses. So I'm just going to apply the I/O to get a new witness for the same function, and then apply the Levin reduction in the other direction to get a new x prime that satisfies the same formula.
What's the role of I/O here?
So the role is to get, I'm starting from one witness for GAP MCSP, and I get a new witness for GAP MCSP. Okay?
Practice to forget everything about that.
Yeah, so
you cannot know which witness you start with.
Exactly. So it's not hard to see just by how we constructed everything that x prime is a satisfying assignment for phi y, and thus age of x is equal to age of x prime. And what we need to prove in order to say that this is a collision is that x prime is different from x. But this is clear by the security of the I/O. And to see it like formally, you can imagine that we start from some collision x1 and x2, and just do this process twice, once that we're starting from x1 and once that we start from x2. And since the formula phi y is the same in both, because y is the same, the truth table is the same, so both circuits C1 and C2 compute the same function. So the I/O must promise us that we cannot distinguish between C2 prime and C1 prime, or from x1 prime to x2 prime. And that's it.
So do you actually need something much weaker, just I/O that like is not breakable by the specific function G?
Yeah. Yeah. You only need like the security of the IO needs to like only be against this like reduction.
Against what? Sorry, against.
Against like this process.
The reduction plus the.
Checking if it's the same.
So even this is impossible.
Yeah.
Yeah.
But like you want to like rule out any reduction, so like, we don't want to assume anything. Okay. Okay, cool. So we have this result that assuming IO with overhead P, gap MCSP with gap P is not Levin NP complete. And now we want to look on it from the other direction. And let's assume that we are able to prove that gap MCSP is Levin NP complete. And by this result, we just get that there is no obfuscation. And of course, I'm lying here. There is the issue of the overhead. So we will only be able to show that if gap MCSP is Levin NP complete with a small gap, then there is no overhead with a small overhead, like obfuscation with a small overhead. But if you will be able to prove that gap MCSP is Levin NP complete for any polynomial gap, then we will get that there is no obfuscation. So if you need a reason to try to prove that gap MCSP is NP complete, this is like a good reason. Of course, we do not know if gap MCSP is Levin NP complete, but there are other problems like multi-MCSP, which we do know that are Levin NP complete. And this gives us a weak lower bound on the overhead of 5. So let me say what multi-MCSP is. Sorry, I will skip it. So multi-MCSP, the input is, again, a string, this time of size n by m. And we think about it as a truth table of a function from log n bits to m bits. So now the function can output many bits, m bits. And the question is, again, what is the minimal size of a circuit that takes log n inputs and output m bits that computes the truth table that is described by T. And again, we can define gap multi-MCSP. We have parameters S and L. We need to distinguish between the case in which there is a circuit of size S that computes T to the case in which there is no circuit of size L that computes T. Again, this problem is in NP, but actually this problem is NP complete. So we know that this problem with this gap is Levin NP complete.
So what's the multi? How multi is the multi?
So here it's M. The circuit is actually most of the gates in the circuit are output gates. Okay, so this is like multi. Okay. Okay, and yeah, and like. I showed you this. Sorry?
How come it's so efficient? The gap is so small?
So this is what we get from the reduction.
This is from your work?
So this is a work of Raoul, Igor, Oliveira, and Loff. And the show initially that multi-MCSP is NP complete. And we like improved a bit the graph. This is like after the improvement. And show that it's actually Levin reduction.
What's multi here? Sorry. Multi.
What if you, instead of using MCSP, do it like some kind of KT complexity type thing? Could you get like some result about IO with IO for Turing machines?
Yeah, so yeah, great question. So yes, you can. We have a result, like the previous result that I showed also worked for time-bounded Kolmogorov complexity if you start from the right assumption, and you can get like lower bound on IO for Turing machines. Like in the paper we wrote, use the NP completeness of conditional time-bounded Kolmogorov complexity to get a lower bound on obfuscation with database access. By the same method, and also you can derive from the NP completeness of DNF formulas. You can get lower bound on proper obfuscation of DNF formulas. You can apply this method on other
But I guess
meta-complexity problems.
KT complexity version, does it only say something about the runtime, but not about like the size of the
So you can define the promise problem of KT such that the gap is both in the running time and in the size of the program, and then you can play with it. Yeah. So we know that this is NP-complete, and also the same proof that I showed you before work also for multi-MCSP. So I showed you the proof, the impossibility result for Levin reduction for gap MCSP, but the same also works for multi-MCSP. The only difference is now that the truth table is like log n2 m bits, and we get a circuit that outputs m bits instead of 1 bit, but the I/O still works, and everything still works. So we don't need to worry about this. And now we know that assuming I/O with overhead P gap multi-MCSP is not Levin NP-complete, but we do know that gap multi-MCSP is NP-complete. So we get this lower bound on obfuscation that says that unless NP is easy, we cannot obfuscate circuit with multi-outputs with overhead less than additive overhead of less than C over log, the size of C, plus any polynomial in the security parameter. So this is like the main result. Okay? And I just want to say that like because we know that if NP is easy, then there is obfuscation with no overhead. By this result, you get that if there is obfuscation with this overhead, then NP is easy, and then you get obfuscation with no overhead. Of course, if NP is easy, you have other problems. And I don't know. Okay. So I want to show you the proof. I want to show you the circuits that we get from this proof that we cannot obfuscate. And we can do it. We can just open up the proof. And to construct the circuits, we just need to, like, you know, the assumption that there is obfuscation and NP is out, construct from it a 1A function, then construct from it a target collision resistant hash function using the work of Rampel, and then like construct a SAT formula from this hash function, and run the reduction, the Levin reduction from SAT to gap multi-MCSP to get the final circuit. And the reduction uses the PCP theorem and chain of reduction, so like we can try to do it, but good luck. I don't think it's a good idea. So instead, what I want to do, if I have time, like I need, okay, 10 minutes, great, is to show you a direct proof, but with worse parameters. So we will not get the lower bound that I promised, but we will see like how the circuits look like. And I'm going to show you the simpler proof. And what I'm going to show you is how to construct a function G and like a family of circuits that we cannot obfuscate with low overhead. So if I lost you so far, you can like now come back. This is not going to use meta-complexity at all. It's just going to talk about cryptography. You're just going to construct a circuit. And it's going to be technical, but in the end, the circuits are very simple. Okay? So I need a PRF. So I need a family of pseudo-random functions. And I'm going to define a function G that takes as input x. This is log n bits input. And outputs m plus 1 bits. So m functions t1 to tm, and additionally a special function t. And we are just going to output the concatenation between these all functions. And this last function t is just going to be a random function. So to sample this function, I'm just going to sample a random truth table. And like given an input x, I'm going to output the x bit of t. So this is easy. And all the other functions are just going to be a one-time paired encryption of t using a pseudo-random function. So for each I, I'm going to sample a random key. And then I'm going to define ti on input x to be t on input x XOR with the output of f using the key ki on x. And the point here is that even if I know the value of t, these functions look like a random function. This is what I need. Okay, so this is the function family, just the concatenation of all these functions for every I and the last function t. And now I want to construct a circuit that computes this function. So I'm going to define M circuits that compute this function. For every index I, I'm going to define a circuit Ci. And the way I'm going to do it is first, for T1, I'm just going to construct a trivial circuit that computes the function T1. So I'm not doing anything smart here. I'm just constructing the trivial circuit of size n, of the size of the truth table of the function that computes this function T1. And I'm going to do the same for each one of the function T1 to Tm, just constructing like the trivial stupid circuit that computes this function. And to compute the last bit T of x, I'm going to use the fact that Ti is just the XOR between a pseudo-random function to T. So I'm going to construct the small circuit that computes the pseudo-random function with key ki, and compute the XOR between the output of Ti to this bit. And this is the way I'm computing the last bit.
How do you know it's small? Why is it?
This is a pseudo-random function.
Oh, I see.
So I have a small circuit that computes it. Okay, so the size of the circuit for each one of the first M outputs, I need like a circuit of size n. This is the size of the truth table, plus something small, a little orphan. So this is the size of this circuit.
So what's the relation between K and N?
Between?
K, the size of the key. And
So it's very small compared to n. I want to do it such that this will be very small compared to the size of the trivial.
I see.
So that requires a very strong PRF or not?
No, it's like polynomially related. Okay.
And what is T? The T of x?
T is just a random function. Okay. Now, this is the circuit Ci that uses Ti to compute this function. I can do it for every j, like using Tj to compute the function. So I actually have M circuits, and like each one uses a different index.
Could you use like a family of functions or already?
It's like a distribution over functions. I have a distribution over functions and like a family of circuits that computes each one of these. And I want to claim that these circuits cannot be obfuscated. This is not going to work, but I will start from trying to obfuscate these circuits. So as a simplified assumption, I'm going to assume something very strong on my obfuscation. The only thing that I want to hide in this circuit is in which index I use in order to compute the function T of x. So I want to assume that the obfuscation doesn't touch the first M circuits. It only obfuscates the last circuits that compute T of x. And the only goal of the obfuscation is to hide the index I. Okay, so it outputs the same circuit as the original circuit, only changes the last part. This is like a very strong assumption. And now, what I know, so the obfuscation outputs something that looks like this. And I'm going to assume that the size of these circuits that computes this T of x is not too large, because if it's too large, then the overhead is large. The overhead of the obfuscation is large. So I'm going to assume that this is small. And what I want to say that if this is small, it means that this circuit must touches each one of the indices, the small circuits here. Otherwise, the obfuscation will not work. And if this touches this M circuit, it means that this circuit must be large, at least of size M, because it touches all of them. So this is going to be the clue.
T of x is random.
Yeah, T of x is random.
Likely that the circuit size is large.
So it's unlikely that this is small.
Correct.
But in the original circuit, we have a way to compute it using a small circuit. Right? This is exactly the point. This is exactly the point. So it cannot be the case that this circuit is small unless it touches at least one of these circuits. So it must touch these circuits in order to have a small circuit, because this is a random function, and we cannot compute a random function. So it must be the case that this touches some of these functions. And moreover, it must touches Ti, because the circuit, we gave it these circuits that maybe knows Ki, but all the other functions just looks random. This is a PRF with a random key. It cannot use T2 in order to compute T of x, because T2 just looks like a random function from the point of view of the obfuscation. So this circuit Tx must touch as Ti in order to compute T of x with a small circuit. But if it touches Ti, and the IO of Cj must touches Tj, it must be the case that the IO of Ci also touches Tj, otherwise we can distinguish. And there is nothing special about J, it means that we need to touch all of them. So the original circuit was of size n by times m plus of n, but the new circuit is at least of size n times m, which is the size of this circuit, plus n, because this circuit needs to touch all of them. So if we just choose n to be equal to m, we get a low overhead of square root of the original circuit. And that's it. Of course, we have this very strong assumption that the obfuscation doesn't touch these circuits. And we use it in the proof. This was important to us.
I think I'm a bit confused. How, given an obfuscated circuit, how do you know that it's...
So I'm assuming that I know that the obfuscation outputs this circuit and doesn't touch it. I see this circuit, and I see that there is a wire from here to here. Okay? I'm assuming that I can check if there is a wire from this circuit to this circuit. This is an assumption, and I need to get rid of this assumption. Exactly. So this is a very strong assumption that I use very strongly, and I need to get rid of it.
And on the proof side, if you choose m to be much larger than n, can you prove the square root to be?
No. So then you can just construct a trivial circuit size that compute T of x without using anything at all, because the trivial circuit that computes T of x is of size n. So this is the best choice of parameters. Okay, so I want to get rid of this assumption, and the way we are doing it is using ideas from the work of Raoul and Loff and Oliveira that show that NP completeness of gap multi-MCSP. So here is the idea. The idea is take this circuit, and remember there is no secrets in these parts. The only circuits that we have is in this circuit. So the idea is just make any internal gate of these circuits an output gate. So we output many output gates for all of the internal gates. Okay? And that's it. That's it. And now, you take this, you try to obfuscate it, you get something. I don't know anything, but I do know that any internal gate here is an output gate, and this has the same functionality, so the output gate also here. And I can find it efficiently because the second wire is connected to this specific gate. So I can efficiently identify in this obfuscated circuit the original circuit. And then it means that the overhead is not large, so I can take everything else to the side and get this exactly the same picture as we had before. And that's it. This is the law. Okay, so this is the proof. And we show that a lower bound on obfuscation using meta-complexity. I want to say that if you can prove better hardness of approximation for meta-complexity problems, then you get better lower bounds. And so this is a good reason to try to get better hardness of approximation result for meta-complexity problems. And also, if you only want to prove that a lower bound on obfuscation, you can show a reduction that uses obfuscation in the reduction. So you only want to prove a lower bound on obfuscation, you can assume that obfuscation exists when you construct the reduction. And if you have obfuscation, you have crypto, like one-way functions, public key encryption, multi-party computation. Maybe it will be useful in the reduction. Actually, we have like a reduction for conditional Kolmogorov complexity that uses witness encryption in the reduction. So maybe it's possible to use this fact.
Go backwards.
Yeah.
So the reason this circuit cannot touch all of them, there are two circuits. So in this
Yeah. So if this circuit is small, then it only can touches like the number of output, like wire it can output is like twice the size of the circuit.
It has to be like very small.
Yeah.
Log size. That's where the log is coming.
No, like it's square root. The overhead we get is square root. Okay, so to conclude, we showed that if you have obfuscation gap, MCSP is not Levin NP complete, and we have a lower bound on the overhead of obfuscation. And like the main thing I want you to take from this talk is that there is a strong connection between meta complexity and cryptography, and the result we get from this connection are in cryptography. Doesn't talk about meta complexity at all, just cryptography, which is interesting. So thank you, and like.
In the meta complexity literature, are there like existing stronger approximation bounds that like on just other variants of things that you just don't know how to prove about, or do we just not know anything that's like much better than like a log hardness of approximation?
I think that for simple things like DNF formulas, maybe Raoul knows better. We know for larger approximation, like polynomial approximation, but.
So for like small target class like DNF, you get like small constant factor approximation, I think, and maybe up to log n. In this work with EG, we get like for the minimum oracle circuit size problem, you can show like polynomial hardness approximation, like pretty close to optimal stuff. But like for multi MCSP, we can't get very good hardness approximation yet.
Cool.
For single bit output, none of the lower bounds are possible.
No, we don't have any lower bound single.
So it was just I missed it, went too fast. So there was something we talked about NP and BPP. Something happened unless NP is in subset of BPP. So what was that about?
So the lower bound, if NP is easy, then we get obfuscation without lower bound at all. Unless NP is easy, we have a lower bound. And like something that you can conclude from this is that if you have obfuscation with very small overhead, then you have obfuscation with no overhead at all because NP is easy.
I see.
All right, let's thank Noam again.
Thank the organizers.
Yeah.